Howdy guys, so today we're going to be having a look at our first video for motion. The first thing we're going to do is have a quick recap of vectors because that's going to help us understand going into projectile motion, how to separate things into their vector components. So on the front here we have one of my favorite cartoon clips from Despicable Me, so Vector, the ultimate bad guy. So vectors and scalars, so this will be pretty quick, so remember to take notes. If you need any extra help with anything, please come and see me. So scalars are represented by their magnitude and their unit only, and vectors are represented by both their direction and their magnitude. So a vector has direction as well as a size. Now a vector quantity is usually denoted with a little arrow above. And these are some common scalars versus vectors. So the things we're going to be looking at, so displacement is a vector, velocity, acceleration, and also force. So these also have to have a direction component to be a correct response. Now if we have to draw vectors, all vectors can be represented geometrically, and we use a direct line segment, so a line with a little arrowhead. And there's a couple of ways that we can add vectors. Basically, the first one is a triangle rule, and here it's really important to remember that it's the head of the first arrow goes to the tail of the last, so we're adding them from head to tail. So here we've got line segment A and line segment B. They don't go the other way, it always has to be head of the first one to tail of the last, and then the resultant goes from the tail of the first one to the head of the last. When we want to find what the actual resultant of that addition would be. Now, when we're adding three or more vectors, we just have to follow that same thing, but we add them together. So here we have A goes down here. The next one, if we go head of the first one to tail of B, that's how that one goes. Then C, we have to go head of this one to tail, and that one comes up here. And then D again goes from head to tail, and then we want to resolve them. We go from the tail of the first one to the head of the last. So the only time you should have two arrowheads touching is when we are actually getting the resultant or the answer of a vector addition or subtraction. Now here we have the addition of 5 vectors, and we're seeing that if we add them all together, regardless of which order we're actually going to add them, we always end up with exactly the same result. So you can see here that the 3 little r's as our resultant is going always in the same direction, so it has the same direction component, and it was also the same length, which in this case, when we're representing vectors, the length is the magnitude. So even though they get added in a different order, the magnitude and the direction is always the same. Now, this is heading into our projectile motion type of questions, so what it actually looks like when we put it into practice. Now, there is a small problem with this diagram. So here we have 2 guys and they're separated by a distance d, and this guy over here is going to throw a ball to the guy on the left. And the actual path of the motion of the ball is going to follow this parabolic line, and it's represented by this solid line coming out of the ball, and this motion here is going to be made up of some upwards motion and some acrosswards motion. And so if we break that down into a vertical component, so the part that's going up, and a horizontal component, the part that's sort of going acrosswards, then we can figure out the resultant one vectorially. Now there is a problem with this diagram. This is how we would assume it would look, but it doesn't follow our rules. So the issue is it's a good diagram to represent a question pictorially, but if we're looking for something in terms of a correct vector diagram that's going to help us actually answer the question, there's probably a couple of problems with it. And the first one is it doesn't follow our rules of having head of the first to tail of the last. So what it should really look like is our little guy here, and we have our motion of the ball, and the initial, this is Vx, and this one, if we go here, I'll put all of them in, and this one over here is Vy, and this is our resultant V. What should happen is this guy here should get moved over here. Okay, so that way we've got the first one, head to tail, and then the last one, we should have two arrowheads overlapping. So it goes from the start, so tail of the first one, to the head of the last. In this case, we have this resultant velocity V actually going in the direction that we know it goes because it does follow that path. So it has to have some horizontal motion to be going acrosswards, and it has to have some upwards motion to be going on, so some vertical part to be having this path here. So this plus this has to equal the path that it actually travels. So hopefully that makes sense as a really quick refresher of vectors, and hopefully it will help you when we head into looking at some projectile motion. Okay, so here we have projectile motion, and one of my favorite games that actually demonstrates projectile motion really well is good old Angry Birds. So, now projectile motion, and a few of you would have covered this before, and hopefully this is a bit of a refresher as we head into some more complicated motion, like circular motion. But again, if you have any questions, make sure you write them down and we can go through them in our lessons. So a projectile is defined as any object that has been projected or launched, so thrown or fired up at some angle into the air near the surface of the Earth. Now, the motion of the object is a curved path. If it doesn't go very high, then the gravitational acceleration may be assumed to be a constant, so our 9.8 meters a second. If we neglect the effect of air resistance, which in this course we do, then the path of the projectile is a parabola, so something that goes up and down and is equal on both sides. So that one is an example, but not a particularly good example, as it's not particularly even on both sides. So when we analyze projectile motion, it relies on the following techniques. So we have to resolve the motion of the two perpendicular one-dimensional motions. So that sounds really complicated, but what it actually means is that when something undergoes projectile motion and it goes up and across all the way up, and then it goes up and across all the way down, it's actually doing two things. It's going up a bit and it's going across a bit each time it moves. So we need to treat these two components of motion independently of each other. So if we consider the actual motion of the ball or the projectile or the shoe if it comes flying off your foot when you're trying to do a kick, if we consider that motion to be a combined effect of the going up and the going across, it'll give you a much better understanding of how we resolve that into the two components. So here is our shoe that's come flying off of our foot. Each time it goes from across to across there, you can see that that's the actual motion that the shoe would take, and that every time it undergoes that change, it goes up a little bit and it goes across. So it has a vertical component in the red and a horizontal component in the blue here. So as it goes up, it starts to slow down, so it's going less up than it is across. And you can see here it's going across, across, across. And it gets this point here where it's not actually going up anymore, it sort of stays still, or it hits its turning point, in which case it starts to then go down. So it's going down a little bit, down a little bit, down a lot, and at the same time, the whole way through, it was still going across. So we can see that they're independent of each other, and one's going up as it goes, it's getting smaller as it goes up, and bigger as it goes down, and the other one is just relatively staying the same, and we'll talk about why that is shortly. Alright, so by resolving this motion, this actual green line, this motion into its two components, it allows us to apply all of the equations and principles of one-dimensional motion that we've already learned. Now, if we're treating it independently, so the horizontal component of motion, if we have a look at a multiple exposure photograph, so here we have our motocross rider going across a jump here, we can actually have a look at the time interval between successive exposures. So if we put lines down, here we go, terrible lines, but if we put lines down, we can see that the time intervals, or how much time has passed between each exposure, is going to be the same. And And so using these vertical lines, we can measure the horizontal distance between successive exposures. So if my drawings were good, what we would see there is that the motion of him going across the ground, or the change in range he's had, so from here to here he might have gone 2 meters, 2 meters, 2 meters, 2 meters, 2 meters, the gaps would be constant. Alright, so we can see that the projectile travels equal distances horizontally during this motion. So what that means is that the horizontal component of velocity of any projectile remains constant throughout the motion, and that's the same for any projectile that we'll come across. So why is it that it remains constant? Well, once an object has been projected, or once it's left the ground, the only force that's going to be acting upon it, and again remember we don't really consider air resistance in this course, so the only thing acting on it is going to be gravity. So force of gravity acts vertically downwards towards the center of the Earth. So if there's no acceleration of the object, it must the acceleration of the object must be in a downwards direction, because gravity is acting downwards, so it must be accelerating downwards. So that's going to be the only one. So if there's no acceleration or change in the horizontal direction, there's no change. If there's no acceleration in the horizontal direction, there can be no change, because if we're not changing anything, if we're not changing either the magnitude or the direction, then there's going to be no acceleration. And in this case, if there's nothing acting on it, if there's no force creating that, like gravity, for example, acting downwards, if there's no force going acrossways, then you're not going to have a change in velocity. So one can't exist without the other. So there is no, if there's nothing acting to slow down the horizontal part, it's going to keep going, and which was what we saw in that first little example with the blue arrows. And we'll come back to that to make it a little bit clearer. But so the vertical component, if we have a look at that same photo, and this time instead of having our horizontal lines, our vertical lines coming down, and we drew horizontal lines across here, we'd notice some interesting things, which is basically the distance traveled vertically between each image. So the vertical distance between successive images decreases as he flies upwards. So he travels further upwards here than he does between here and here, and again it's much smaller interval here, and then he starts to go down the other way. So the vertical distance between the images decreases on its upward flight and increases on the downward flight. And as he's moving down, the spacing again gets bigger. So when the spacing between where the spacing between the horizontal lines was equal, the vertical distance basically decreases on the way up and increases on the way down. So what we can gather from that basically is saying that the vertical distance traveled between successive exposures in equal time, it varies. So therefore the vertical component of velocity actually changes during the motion, which is again what we saw in that first diagram. As it goes up, starts to fly up, it goes a long way vertically, and then it goes a little bit less until it reaches that turning point where it's not moving, and then it changes direction and starts heading downwards. So if we consider this, a bullet is fired from a gun at the same time at which another bullet is dropped from the same height. Which one hits the ground first? So if one's shot out of a gun at the same time as one is just dropped out of someone's hand, what's going to happen? Well, the answer is that they'll both hit the ground at exactly the same time. Now, one of them will hit right at your feet, and one might hit a few hundred meters away. However, they'll both hit the ground at exactly the same time. So, even though it sounds ridiculous, it's true, and we're going to have a look at why that is. So, why is the vertical velocity the same as the velocity of a free-falling object? So, this is a multiple exposure again of two tennis balls, pretty much in that same scenario we were talking about with the bullets. So one of them is going to be dropped from hand height, and the other one would be projected in some way. And so this one is going to be vertically just under the influence of gravity, whereas this one's going to be thrown horizontally, almost like a bullet. Now, what we can see is that the vertical positions, if we put lines across the middle of each ball, the vertical positions of the balls are the same at all times. So even though it seems strange that we could drop one straight at our feet, it would hit the ground at exactly the same time as the one that we actually fired or projected. So the distance fallen between any of the two exposures is the same, which means that they're falling at the same rate. So the vertical component of the projected ball is identical to the one-dimensional motion of a ball that's just falling straight downwards. Okay, now velocity. This slide pretty much sums everything up that we've covered in this part. So if we look at the actual velocity, so the actual motion of a projectile, okay, its motion is in a direction that's a tangent to that parabola. So you can see it's slowly following on this red line here. Now, these are some dot points that will sum all of the key points up. So the velocity vector, so v, is always at a tangent to the parabola, and the direction of the velocity changes with time. So our little arrow is going to be going up there, it's going to be a slightly different angle here, a slightly different angle here, a slightly different angle here, and so on. Now the magnitude of the velocity changes with time. So here it's gone up a long way, a little bit less, a little bit less, and so on. So the actual magnitude changes with time. Now the horizontal component, alright, so in this case we're looking at VH, or V horizontal, or V in the X component, V in the X direction, is constant throughout the motion. So if we look at each of these little VX's or V horizontals, they're all to be exactly the same, because the only thing, remember, acting on a projectile is gravity. So nothing is acting in that horizontal direction, so that is going to remain constant right throughout that motion. Now the vertical component of that vector, so Vy or Vv, V for vertical, changes with time. And it decreases while the projectile is rising, so it starts going up a big bit, a little bit less, a little bit less. Once the projectile passes its highest point, it then increases in downwards direction, so it changes as it goes. Now at the highest point of its flight, the velocity of the projectile is only in the horizontal direction, because it's reached its turning point. It's not moving either up or down for a split second, so the only motion it would have is straight in that horizontal direction. So at this point, the vertical component of the velocity is 0, and the actual velocity, so the path that it actually takes, is equal to its horizontal velocity only, because there's nothing else acting on it right at that specific point. Now, if we know the vertical and horizontal components at any point along its flight path, then we can actually find the v, alright, the actual velocity at any point, by adding up these two components. So what that looks like is, to find the v, or to find the velocity vector at any point in a projectile's flight, we add up the horizontal and vertical components of that motion vectorially, and we'll be able to figure out the magnitude of v. That's about what we wanted to cover. So the next video we'll be looking at is how to apply Newton's equations of motion to do some projectile motion calculations. I hope you have written down any questions that you had, and I will see you in class.